All right, let's get right into it. Today we're looking at a paper called Demystifying our ARM SME to Optimize General Matrix Multiplications. It's by Deng, Yang, Fang, and Dong from the National University of Defense Technology. And here's the hook. Everybody is racing to optimize matrix multiplication, or GEMM for AI. But if you're on new Apple Silicon or any modern ARM server, you might be leaving, well, a massive amount of performance on the table.
That's exactly it. It turns out current libraries, and we're talking about the big ones, like OpenBelize, even Apple's own Accelerate framework, they're just not fully using the new ARM Scalable Matrix Extension, or SME.
Okay, so what's the breakthrough here?
This paper introduces a new open source library called MPGEMM. And it actually outperforms Apple's own, vendor-optimized library. We're talking 1.23x faster on an M4 Pro.
Wow.
And the secret sauce really is three things. First, cache partitioning that specifically targets the shared L2 cache. Second, some really novel packing schemes using on-the-fly transposition. And third, this is the big one, micro-kernels that use 4-vector load instructions.
And that's the part that gets that huge bandwidth jump.
That's the one. It goes from about 230 gigabytes per second to 900.
So if you're doing machine learning on Apple Silicon or ARM servers, this is how you unlock what the hardware can actually do. Welcome to AI Paper Podcasts.
Okay, so let's zoom out a bit. We always talk about GMM, General Matrix Multiplication, as being, the engine room of deep learning.
Right.
But usually that conversation is all about NVIDIA, CUDA, H100s. Now, ARM is in the mix with the M4 Pro and this SME architecture. What exactly is SME? It sounds like just another vector extension.
It does sound like that, but it's fundamentally different. We're all used to SVE, the Scalable Vector Extension, great for standard SIMD stuff. But SME, the Scalable Matrix Extension, that's ARM's direct answer to something like a tensor core.
So it's not just wider registers. It's a whole separate unit sitting there.
It's a new architectural extension built on top of SVE, and it has its own dedicated hardware state. The M4 Pro, which is what the paper focuses on, has this 2D tile-based accumulator they call ZA storage.
ZA storage. Yeah, on the M4, it's a 4096-byte space. And the magic of SME is that it lets you do outer product instructions.
Okay, let's pause on outer product, because most of us just remember the dot product from school. Row times a column gives you one single number.
Right, the dot product collapses everything down, super inefficient if your goal is to build a whole matrix. The outer product is the opposite. You took a column vector, multiply it by a row vector, and you get a whole matrix out of it, a rank 1 update.
I see.
And SME accumulates that update directly into its ZA tile. So you're building the result in these 2D chunks instead of like one element at a time. It's way, way more efficient for matrix math.
Okay, I get the hardware. It's a specialized unit for matrix math. But here's my question, my skepticism. We already have libraries for this stuff. Apple Accelerate ships on every Mac. There's OpenBlast, Alibi, XSMM. These are mature projects. Why do we need another one? Where's the gap?
The gap is surprisingly large. And it's really because this SME hardware is so new. The paper points out that the existing open source libraries, they're mostly optimized for small matrices. They just don't scale. Or, in the case of something like OpenBlast, they just fail to use the specific SME2 multi-vector instructions. They're basically driving the M4 like it's an M1 or an M2.
And Apple, they built the chip. Surely they know how to get the most out of it.
You'd think so, right? And to be fair, Apple's Accelerate is the reigning champ. It's closed source, highly tuned, and it usually smokes everything else. But what this paper found is that even Accelerate kind of hits a wall on these really, really large-scale workloads.
Like the big language models?
Exactly. Think Llama. Think DeepSeek. The matrices are just massive. And that's specifically where MPGEMM managed to beat Accelerate.
That is a bold claim. Beating the vendor on their own silicon? That implies Apple left something on the table. So let's get into how they did it. The paper points to two huge bottlenecks. The first one is the cache problem.
Right. And this is where you have to really understand the M4 Pro's specific architecture. On this chip, the SME unit, the thing doing the math, it shares its L2 cache with the CPU cores.
And that's a 16 megabyte L2 on the P cores, right? 16 megs sounds like a lot of space. Why is that a bottleneck?
It is a lot, but there's a catch, a very subtle one. The paper found, through a lot of micro-benchmarking, that there's this really strict memory ordering relationship. If you put your matrix data on the stack, you get pipeline stalls.
Stalls? Just from using the stack? Why? Is it a coherence thing?
Precisely. It's about how the CPU core and the SME unit talk to memory. The SME unit really, really wants its data in dedicated heap memory. If you use the stack, they start stepping on each other's toes, trying to figure out who owns what data, and the whole pipeline just freezes.
So just by declaring your variables in the wrong place, you're kneecapping your performance? That's tricky.
It is, and it's the kind of thing generic libraries miss. But the bigger problem is the working set. Current libraries use these simple three-level nested loops. They might pack one matrix, say matrix A, but they leave matrix B totally unpacked.
And I'm guessing that's a problem when matrix B is huge.
It's a disaster. As soon as that unpacked matrix is larger than the L2 cache, performance just falls off a cliff. You get TLB misses, cache thrashing. It's a mess.
Thrashing is the perfect word. It's like trying to cook a massive dinner in a tiny kitchen, right? You're just constantly running back and forth to the fridge because you have no counter space.
That's a perfect analogy. And because the existing libraries don't model this shared cache behavior correctly, they're always running to the fridge, which is main RAM, and it is slow.
So how does MPGEMM fix this kitchen problem?
They switched to a 6-level blocked algorithm, but instead of just guessing at the block sizes, they use an analytical model to calculate the tiling parameters, CNC, and NACIA. But here's the really fascinating part. Their goal is to make sure the working set fits strictly within an 8 megabyte effective window.
Wait, hold on. You just said the cache was 16 megabytes. Why are they only using 8? Why leave half of it empty?
That was one of the key discoveries from their micro benchmarks. The physical cache is 16 megabytes, sure, but the actual bandwidth you can get saturates and then drops if your working set exceeds 8 megabytes.
Huh.
It seems to be a sweet spot. If you try to use the whole 16, you start competing with other system processes, or maybe hitting associativity limits that actually slow things down. So they treat that shared L2 as their main target and aim for that 8 megabit window, essentially bypassing the L1 cache strategies you'd normally use.
That is so smart. You don't fight the hardware. You listen to what it's telling you, even if it contradicts the spec sheet.
Exactly. And getting that cache discipline right is what sets up the solution for the second bottleneck.
Okay, let's talk about that because this is the number that just jumped out at me from the intro. You said they went from 230 gigabytes per second to 900. That's almost a 4x jump on the same hardware. How is that even possible?
It all comes down to what they call load granularity. This is just a classic example of software not keeping up with what the hardware can do. The SME unit has these things called Z registers.
Right.
Most libraries, they load one Z register at a time. That's 64 bytes. Maybe some of the better ones load 2, so 128 bytes.
So they're fetching data in these little SIPs. Why is that bad?
Because the memory bus on the M4 Pro is like a fire hose. And they're trying to fill a bucket with a teaspoon. Their micro-benchmarking showed that loading 1 or 2 registers at a time leaves the bus mostly empty. It's just inefficient. The only way to actually saturate the bus is to load 4 Z registers at the same time.
So 256 bytes in a single go.
In a single instruction.
That's the grocery analogy again. I can go to the car and bring back 1 bag at a time and I'm just walking back and forth all day. But if I can carry 4 bags at once, I'm done in a quarter of the time. The car's the same distance away, the bags weigh the same, but my throughput is quadrupled.
That's exactly it. You're filling the channel. But there's a critical link here. This only works, this super high bandwidth, if the data locality is good.
So you have to be under that 8 MB cache limit we just talked about.
You have to be. If you go over 16 LD, even with 4-way loading, the bandwidth craters, it drops back down to like 145 gigabits.
So the cache optimization enables the bandwidth optimization. They're totally linked.
Precisely. You can't just flip a switch for 4-way loading if your data isn't sitting right there in the cache to begin with.
Yeah.
And that decision dictates their entire microkernel design.
We hear microkernel and think operating systems, but in GEMM it's different, right?
Yeah. In this context, the microkernel is just the innermost loop of the whole computation. It's the tight little block of assembly code that actually does the multiplications and additions. Everything else is just data setup for this one little kernel.
And most libraries use what, a 32 by 32 block?
Yeah. OpenBLEA, Cloudy AI, they use a 32 by 32 microkernel shape. And MPGEMM changes it to 16 by 64.
Okay, why that specific shape? 16 by 64. What's magical about that?
The number 64. A 64-element dimension aligns perfectly with loading 4 Z registers.
Of course, because 1 Z register is 64 bytes.
Exactly. This shape lets them use that 4-vector load instruction to just hammer the outer product throughput while keeping that data pipe completely full. They're literally matching the shape of the math to the shape of the memory bus.
That makes a ton of sense. But there's always a trade-off. Moving all that data around, packing it so it aligns perfectly into these 16 by 64 blocks, that costs time. That's overhead. How do they deal with the packing problem?
This is where the paper gets, just really creative. You could call them cool hacks or maybe more formally hardware accelerated packing. They have two big innovations here. First is on-the-fly transposition for matrix A.
Transposing a matrix is usually slow, right? You're reading rows, but writing columns, jumping all over memory.
Yeah, it's called a gather operation, and it's basically the worst thing you can do for memory access. It absolutely kills performance. But they use the hardware itself to cheat. Remember the ZA tiles, that accumulator storage?
Yeah.
You can access it horizontally or vertically.
Oh, I see where this is going.
So they load rows into the ZA tile, which is fast and sequential. Then they just read them out as columns. They're using the computation unit as a high-speed data shuffler.
That is ridiculously clever, using the math coprocessor to fix the memory layout.
It is. And for matrix B, they use a different trick. First round online packing.
Online packing, so packing while you're computing.
Exactly. The M4 Pro is a superscalar chip. It can do multiple things at once. And critically, the SME unit doing the math and the load store unit moving memory are independent. They can run in parallel.
So while the SME unit is busy crunching numbers, executing those FOMAPI instructions, the load store unit is already packing the next block of matrix B into the buffer.
Precisely. They hide the packing cost completely behind the math.
The packing is effectively free. It's happening during cycles that would have been wasted anyway.
Yes. It's like having a sous chef chopping veggies for the next course, while the chef is plating the current one. The cooking never has to stop.
Okay, let's shift to the real world here. Most people doing AI aren't running pure FP32 anymore. It's all about mixed precision FP16 INT8. That's what LLMs actually run on. Does this library handle that, or is this just a cool FP32 experiment?
Oh no, it absolutely handles it. And SME actually shines here, because the architecture is built for this. It lets you take low-precision inputs, like FP16, and accumulate them into a high-precision FP32 tile. So you get the speed of low precision without losing accuracy.
So how does their approach change for FP16?
They have to get creative with the layout again. To keep their four-way loading strategy, they treat two FP16 elements as if they're one logical FP32 value, and they use a special ZIP instruction to interleave the data really efficiently.
And the performance payoff for that?
For FP16, they're seeing a 1.7x speedup over Locality AI, which is another solid ARM-optimized library. But the INT8 results... The INT8 results are just wild.
How wide?
They reach 94% of the theoretical peak performance of the hardware.
Wait, 94%?
94%.
Yeah.
We're talking something like 7,800 giga operation per pistol.
That's insane. I mean, in software, if you get to 70 or 80% of theoretical peak, you pop the champagne. The rest is just assumed to be lost overhead. Reaching 94% means there is almost zero waste. They are running that chip at the absolute speed of light.
It's an incredible level of efficiency. It really just shows that if you code to the metal, if you strip away all the layers and program for the hardware's specific quirks, the M4 Pro is an absolute beast.
Okay, so let's look at the scoreboard. They tested this on real models, DeepSeek, and Llama. These aren't random numbers. This is actual AI inference. How did MPGEMM stack up?
So two categories. First, against the other open source libraries, OpenBlayS, Claddy AI, LibX SMM. And on large matrices, MPGEMM just destroys them. We're talking speedups from almost 4x to 5.7x.
5.7x. That's the difference between a model taking 5 seconds to respond versus taking 1 second. It's huge.
It is. And the reason is clear. The others just don't handle the cache hierarchy well for big data, and they don't have that crucial SME2 multi-vector support. They're leaving all that bandwidth on the table.
Okay, and now for the boss fight, Apple Accelerate.
This is the big one, yeah. Accelerate is amazing. It's highly, highly tuned, and yet MPGEMM still wins by 1.23x on average for these workloads.
But why? How does a research paper beat the vendor? Apple has, effectively infinite resources.
I think the classic case of generalization versus specialization.
Yeah.
Apple's library has to work well for every matrix shape, every size, every possible edge case. It has to be robust.
Right.
MPGMM's analytical model for the L2 cache is way more aggressive. They tailored everything for that 8 MB sweet spot. And that 4-vector loading strategy is just perfectly tuned for the M4's specific memory bus.
So Apple is maybe playing a little safe to guarantee stability. And these researchers just said, let's see how fast this car can actually go if we strip out the back seats.
That's a great way to put it. But it's also just a true masterclass in optimization. It proves there's still so much room for innovation, even in an algorithm as old and well-studied as matrix multiplication.
So let's wrap this up. What's the main lesson here? What should our listeners take away from this?
The lesson is that hardware is only as good as the software driving it. The M4 Pro has this Ferrari engine inside. That SME unit is incredibly powerful. But most standard libraries are driving it like a sedan. They're treating it like a normal CPU. MPGEMM shows that to actually race it, you have to understand the hardware intimately.
It really feels like we're moving past an era where generic optimization is good enough.
I completely agree. The bigger picture here is a move toward these custom microkernels. As chips get more and more specialized, with things like ZA tiles or tensor cores, your generic loop optimizations just aren't going to cut it anymore. You have to know about four-way loading. You have to know about the cache sharing between the cores. You have to get down to the register level.
And for anyone listening who wants to see exactly how they pulled off that on-the-fly transposition trick, I really do encourage you to check out the paper Demystifying ARM SME. The assembly code breakdowns are fascinating. Well, that's it for today's deep dive into ARM optimization. Thanks for listening to AI Paper Podcasts.
See you next time.